I'll be talking about the proton. Okay, a proton is a component of the atom, according to quantum mechanics. The question is whether it is an object, whether it's a thing. Okay, and as far as we know, we can't do physics without things. You need things in order to illustrate a mechanism. Okay, and that's what physics is about. Anyways, it turns out that after over 100 years of quantum mechanics, not a single mathematical physicist, not a single quantum mechanic out there can illustrate for you the proton. They have no idea what it looks like, what it is. And so the question comes up, is there something wrong? I mean, after 100 years of smashing atoms, doing their equations, simulations with computers, etc. With all this, they cannot figure out what a proton is. And so something seems to be wrong. And the question is, can they explain to you a theory until and unless they have a proton? Theory about atoms, right? Imagine you tell me a theory, for example, of leprechauns, and you start saying, well, the leprechaun went on the other side of the rainbow and he found a pot of gold. And hold it, what is a leprechaun? I've never heard of the word. I don't know what a leprechaun is. Can you show me what you mean by leprechaun? And you cannot say, well, I've never seen a leprechaun, I don't know what he looks like. Well, I mean, I don't care what he is in reality. Okay, I need to know what you mean every time you pronounce the word leprechaun. So I need to see the object that you have inside your head so I can follow your train of thought. I can follow your theory. And that's the problem with quantum mechanics. They start talking about everything already in motion. That proton does this or does that. And they never illustrate the proton in a way that is rational, that they can defend. Okay, that's the problem. They start already the movie in motion in the middle of the movie. They never start on the first frame showing you what a proton is. That's the issue. Okay, so when you look up the word proton, like in images, Google Images, this is what you get. You get a whole bunch of images there, and they say that's it. As you can see, most of them just show an atom, or half of them at least. And it turns out, if you look up the hydrogen atom, you get more or less the same pictures. You get something like that. Okay, and so the question is, what's a proton? And is it equivalent to an atom? I hope not, right? Because I hope these are two different entities, right? Now, most of the time you get something that looks more or less like this. Okay, this is lately what you're getting. You're getting this 2 up quarks and 1 down quark. And as you can see, it's got this gray thing encapsulating those 3 balls in there. Right? We're assuming they're balls. They look like balls, 3D balls, image with in a 2D platform there. And so the question is that a proton right there? I mean, which one is it? Because there we see too many things. I just wanted to see the proton all by itself. And I guess, is this what I'm supposed to be seeing? Is that the proton? Just the ball that encapsulates everything? Is that what a proton is? A ball? Okay. And then there's other problems with this, right? As you can see, it's got these little white squiggly lines. And those are the gluons that mediate the strong force. And there's, what is that? What are those little squiggly lines? And it turns out that it's all of the above. It's a bead. It's a flux tube that extends outwards from one quark to another. So the quark sends a particle, but then it turns somehow into this slinky that covers the whole space between the 2 quarks. Then it turns into a bed spring, as you can see, some curlicue there, right? And finally, they have it turn into a rubber band that when it stretches too far, it breaks and creates 2 more quarks. All magic, all done by magic, right? So the gluon is all of the above: a bead, a flux tube, a bed spring, and a rubber band. And there you see, the one on the right there. Are we talking about a trace? Is that what that squiggly line represents? Is that an itinerary? Is that what we're looking at? Or are we looking at a bed spring that stretches from one quark to another? Those are two different, notions of a gluon. And as you can see, you can't rationalize the gluon, let alone the proton. I mean, so far we don't know what they're talking about. What is a proton? And we'll have this fellow, and he's a mathematical physics. He's going to tell you right off the bat, what a proton is. So listen to him. Okay, here it is. Listen carefully.
We don't know what a proton looks like. You were probably told that it looks like a sphere of charge inside of an atom. But this isn't correct. At university, you were probably told that a proton is a combination of up and down quarks. But this is also wrong. Physicists are still struggling to fully understand what exactly a proton is.
Okay, so now you know exactly what a proton is. It's whatever. They're still trying to figure it out. Okay, so not having much luck with the physicist, the so-called physicist, mathematical physicist, let's go to the AI. Let's see what the AI has to say about these thingies called protons. Okay, here it is. Proton is a quantum object. That's what it is. Quantum object, whatever that is. Quantum object refers to what? Any system that behaves, talking about behavior here, right, according to the principles of quantum mechanics. Classical physics, meaning rational physics, imaginable physics, right, doesn't accurately what? Describe their behavior. Quantum mechanics are required to what? Explain them. So we're not going to point to a chair and describe the chair. We're going to explain the chair. Okay, that's what they're going to do. And they're saying that proton is a quantum object, whatever that is. Let's find out. Let's find out what a quantum object is. Here we have quantum object. It just goes to properties. It says it has wave-particle duality. Quantum objects can behave. They're talking about behaviors, right? As both waves and particles. Light can behave as a wave when traveling through a prism. Also as a stream of particles, photons, when interacting with matter. And so it's got all these properties, superposition, entanglement, and when you measure them, you get one state collapsing into another. In other words, the man turns into a woman or a woman into a man, right? Right off the bat, without any motion. They just convert, morph, okay, instantaneously. And they change their state. Okay, yeah, sounds like witchcraft, like black magic, not like science, right? But that's how they present their case. Okay, that's how they start. And the AI continues, says, like all subatomic particles, protons are governed by the principles of quantum mechanics, meaning irrationality. This means that they can behave as both a wave and a particle. There you see them at the bottom, the wave and the particle. So which one is it? Are those two identical? I mean, it's either a wave or it's a particle. How can it be both? And yeah, they said both because they covered all the bases. That's what they did. Then it said protons have a spin of half, with whatever that is, because as we discussed in the prior 2 weeks, they have no idea what spin is. It's not like a top. So the best way I can illustrate spin half is having the ball there rotate halfway and then stopping. I guess that's a spin half. I mean, we don't know. We have no idea what a spin is, let alone a spin half. It's just a number. They needed a number to put in there. They call it spin, which confuses the hell out of everybody because everybody thinks that spin is like a top, and they do illustrate it as a top, but then they deny it at the end of their presentation. So everywhere you will find the spin property, this attribute, right? You'll find it as being like a spin of a top. That's how you'll find it. And then they deny it. So we have no idea what spin is, but as you can see, so far we have black magic because the proton behaves as a wave, behaves as a particle, it has spin half, but we don't know what it is. What are they talking about? I mean, I need for them to start by pointing to an object, a thing. What are they going to point to? 3 quarks connected by gluons? That's not a thing. That's many things. I need the thing that they're going to call proton. Okay, if they're going to be moving the proton. So don't show me what's inside the proton. Show me the ball, if that's what a proton is, right? If it's a cube, show me a cube. If it's a cone, show me a cone. Whatever you think a proton is. And again, I don't care about Mother Nature's genuine proton. That's not what we're talking about here. We're talking about your proton, okay? We're saying, you're going to give me a theory. You're going to tell me about mechanisms in quantum mechanics that have been proven, discovered, certified, verified, etc., right? So I want to know what you have going on inside your mind. I want to know your proton. I don't want to know Mother Nature's one. I want to know yours. I want to know your God, not the God, not the real God that's out there in heaven. I want to know what you think God is. Show me your God, then you can do whatever you want with God, right? That's the way it works. And here you can see this proton turning into a wave. And again, we have this fellow, this mathematical physics. He's going to tell you exactly what a proton is. It's some kind of wave, or has wave property, or turns into a wave, morphs into a wave. Here it goes.
While the mathematics of quantum mechanics allows us to make excellent predictions, it fails to definitively describe what a quantum object is. So the question remains, what is a quantum wave function? And if this wave function actually exists, what happens to it when we measure it?
So we have this proton. It started as a ball with 3 quarks in it connected by gluons, and somehow it morphs into this wave, a wave function. They're talking about math. And so the question is, how did the particle convert or morph into a wave, or vice versa? Because they have the wave function collapse, meaning it collapses and turns into, well, he says, he doesn't know what it turns into. But the way they explain it is that it turns into this little ball, localized ball, as soon as it hits something, like your probe or whatever. So, or your eyesight observer, all right? So we have a problem because we don't know what they're talking about. They can't point to their object and keep it still and say, this is what a proton is. They have the already behaving, comporting. They're doing something. This thing is already acting. It's turning from a ball into a wave, wave into a ball. It spins but doesn't spin, and so it's doing all these things. It's changing its state from one state to another. It has all these states, and then suddenly it collapses into one state. So they have all this magic. That's all. All the explanations of quantum mechanics are magical. They're irrational. It's okay for Hollywood movies. That's great. This doesn't belong in science. That's the issue. Okay, and so the only thing they have to tell us about waves, which I covered the other day, is this, and that is whether the wave extends, right, or travels from the Andromeda galaxy. For example, here you have this wave. It extends, or does it travel like a little sailboat, a discrete little sailboat? Which is it? So if photons, electrons, protons, neutrons, whatever, is made of waves or travels as waves, are we talking about a wave that extends, or a little sailboat that is discrete, has a beginning and an end, and travels all the way down here? Which is it? So they always say it's all of the above. That way they cover all the bases. And so we have no idea exactly what they're referring to because, again, they never worry about the physical part. The physics, part of physics, they just want to do math. And with math, you don't get an idea of what they're talking about. And here you have the problem. The problem is that to this day, they have no idea what an object is, let alone a quantum object. They have to define what an object is first, and here you find in the Wikipedia, in physics, an object is an what? Identifiable collection of matter. Well, that's already wrong because matter is a collection of particles, of things, of objects. So to say that it's a collection of matter and matter is a collection of objects, all you have is a circular definition. It says, which may be constrained by an identifiable boundary. Okay, that means it's got a boundary. Yeah, great. And may move as a unit or translation, rotation, spin, I guess, right, in three-dimensional space. A physical body as a whole is assumed to have such quantitative properties as mass, momentum, electric charge, other conserved quantities. So immediately they move on to math. Okay? We don't need that. I just need to know what an object is. I don't need to put numbers into the word chair. Is the chair an object? Why is it an object? Well, because it has shape. That's why. And I don't need to know what equation or how much mass it has or what equation I can apply to a chair. So why do they bring math where it's not needed, where it's irrelevant to the question being asked? And yeah, dictionary.com, anything that is visible. The word anything already throws it off because anything is the word we're trying to define. And they're saying, what is anything? Anything is anything that is visible. That's all they said so far. Okay? Or tangible. So again, they say it's see, touch, criteria, and those are both irrational. Because first, it invokes another object. Second, not all objects can be touched, certainly, or seen, right? We can't see atoms, for example. And certainly we cannot see the chair that's on the other side of the universe, Klingon hands over there, and for sure you cannot see the chair I'm thinking about in my mind. So is the word chair, does it represent an object, yes or no? And so what they have in the dictionary is no good. We can't use that in physics. That's okay in ordinary speech, but not in physics. And it says the thing, a person, or a matter to which the thought or action is directed. Again, they think that an object is just something you can talk about, or subject of the sentence, or noun, or whatever. Not for physics. In physics, the word object is very special because you can't do physics without it. And so you had better define the word object properly. And here we have another fellow, another so-called mathematical physicist, and he says the following. He says, objects are described completely by what? Their mass and their electric charge. Even though photons are known to have neither one, right? Or at least that's what the mathematicians say. So I guess photon is not an object, not a thing, okay? Whatever's traveling is not a thing. We have motion without object, without ball. Mass and electric charge are the only intrinsic properties of everyday objects. Both mass and electric charge are defined by the acceleration they produce around them, and the state of objects' varying aspects can be described, not defined, but described, right? Using momentum and position and all other stuff. Yeah, this is the problem. They never defined the word object, and it turns out that you can't do physics without object. Should be the word that is defined in every textbook of physics. That should be the first word that should appear there. We should know what an object is. Not a single mathematician, mathematical physicist, which call themselves physicists, has any idea what an object is, what a thing is, and that's why they do physics without things. Okay? Okay, can we use the quantum proton? I mean, are there any problems with it? And for this, we have to go to the history of the atom. A brief history of the atom. Okay, so here it is, very quickly. 1904, we have Joseph Thomson. He proposes the plum pudding model of the atom. Quite famous, really. And another Japanese fellow, his name is Nagaoka, proposes the Saturnian model there of the atom. You can see it there at the bottom. The negative electron were rings, okay, that just went around like hula hoops around the some center, some proton. Not a proton. They didn't have the notion of the proton yet, but he was thinking of these electron rings, okay, just like Saturn. By 1911, Rutherford runs his backscattering experiments and concludes that there is a nucleus, okay, at the center of the atom. By 1913, Bohr, using Planck's quantum, which he came up with in 1900, right? He puts these electron beads, these little tiny beads, negative beads, in specific orbits, which today are known as orbitals, these energy levels. And for some reason, these little beads cannot fall to they can fall within certain energy levels, but not beyond. In other words, what stops an electron from falling all the way to the proton or the nucleus, right, is the energy level. And again, energy level is not a thing, so you cannot say the energy level stopped the electron from falling to the proton. So they never answered the question. They just mathematized it and continued. By 1924, Louis de Broglie proposed that the electron is also a hula hoop, pretty much like Nagaoka, but he had them in, integral waves, okay? And so thus is the way the planetary model of the atom was born, and that's what we have today. But none of these, whether classical physics or quantum, can explain to you why the electron doesn't fall to the nucleus, okay? Or why it doesn't automatically fly away. Like here's what I'm talking about. Here you have the electron. It's going to go around the proton, right? This is the alleged hydrogen atom. And the question is, why doesn't it lose energy, right? Whatever energy is, and fall to the nucleus? This question was never answered. They just said, look, there are these energy levels, these orbitals, and the electron must stay within that. But that's a description. It doesn't tell me what the mechanism is. And then they have a question that nobody, I guess, asked, or they never answered for sure, and that's, why doesn't the electron fly away? Okay, so we have this electron bead going around the nucleus, and why doesn't it fly away spontaneously? What's keeping it tied to the proton? So we don't know why it doesn't fall to the nucleus. After all, the proton is positive and the other one's negative. Positive attracts negative. The electron bead should fall to the proton bowling ball, which weighs a lot more, 1,800 times as much, right? And then at the same time, you're wondering, well, if it's going around, why doesn't it just fly away spontaneously? What prevents it from? Why do we need ionization, someone to stimulate the electron to have it fly away? And so they never answered these questions. Here we are 100 years later, they don't have answers to these basic questions, which in fact triggered the religion of quantum mechanics. Okay, so they have this explanation. You can say it's a mathematical description. That's all it is. Neutron in beta decay turns into a proton and electron plus something else, which is an antineutrino in this case, right? So the question is, how did they blend? I mean, how did the electron fall to the proton to create the neutron if you have these energy levels preventing it from happening? Okay, you have all these energy levels. You have the electron there, right? And every 15 minutes, a neutron converts into a proton and an electron plus the antineutrino, and vice versa. These guys can turn into a neutron. Well, how do they do that if the electron is prevented from going to the proton, getting near the proton because of these energy levels, whatever those are, right? And so, what is the physical mechanism? And they never answer that question. And so we have a problem because they're not answering any of these questions. And they're saying that they proved everything, they discovered everything, they get all these Nobel Prizes, and no one answers any of these questions, which are really basic to quantum mechanics. We're still 100 years later trying to figure this out. I mean, not us, but the mathematicians, right? Okay, so here we have one fellow, and he writes a lot in Quora. His name is Victor Thoth. And just like the Egyptian god Thoth, and so I think he's got the right name for who was the god of math, right? And I think it's the right name for this fellow. Anyways, he says, the meaning of the word quantum changed several times over the past century. So we started with a quantum, which was a bundle of energy, and now this fellow is going to tell us that that's changed in these last 100 years. So you got to pay attention to that because they talk about quantum computers, and so on. There's no more quantum. Quantum died several decades ago, okay? And here it is. Originally, it literally meant what? Light electromagnetic radiation is emitted in discrete quantities. That was your bundle of energy, okay? What happened, the quantum theory was born, and then didn't say anything about the nature of light itself, but about, or about particle theories of matter. So in other words, there was no matter, no object involved. It was just math, That's what he's saying there, right? Then came the quantum revolution when you have Heisenberg there and Schrodinger. They came up with wave mechanics, and suddenly the particle turned into a wave. In fact, before that, in 1924, you had Louis de Broglie come up with his wave notion of the electron. And so matter was also, waves. So we have waves and particles, both representing matter and subatomic carriers like photons, etc. Right? They were about quantities that show the oscillation gain energy in this oscillation gain energy in discrete units. In order to truly understand this, the math is absolutely essential. Yeah, it's all math and no physics. That's the issue. We have no idea what they're talking about because they cannot illustrate any of the things that they're talking about. That's the issue. All they do is just talk about math, and they try to simulate it with little balls and little waves. Anything that they could put in there, but the waves and the little balls and whatever they put on the screen has nothing to do at all with reality. But they said they proved it, that they're balls, and that, for example, a proton is made of 3 little balls called quarks. Where did they get this? This is just math. It's got nothing to do with reality. And but then thought tells us that there is no more quantum. They got rid of it with the quantum field theory. They introduced fields, which has to do with waves, and they got rid of the particle completely. They don't use the particle anymore. The math is all geared towards waves because they need to tie the field of quantum mechanics with a field of general relativity in order to merge the two theories. That's the issue. Okay, so here, quantum field theory, particles transform into one another or emit or absorb other particles. So the key word there is transform. Yeah, they just pull out the magic wand and they transform. They transform how? By what mechanism? Don't give me math. Don't tell me here's the energy and here's the mass or the charge. I want to see a mechanism, and you'll never see a mechanism illustrated. Whatever they illustrate is 150% irrational. The fundamental physical entities are ever-present fields. So now we no longer have particles. Now they're being replaced by fields. The excitations of these fields again come in discrete quanta that are spatially localized. We perceive them as particles. So now they're saying a vibration of a field, local vibration of a field, that's what a particle is. Okay? So quanta are particles. No, not really. Or you could say, yeah, quanta probably is the notion that it's a bundle of energy. That's the notion of a particle. They are excitations of quantum fields. So they try to cover both bases, right? They said they're particle, they're numbers that are vibrating their energy, which is just a value, right? That's vibrating it, but it's a little bundle of energy, whatever energy is, because we have no definition of energy either. Or it's a concept anyways, so you can't say that it turns into a particle. But then they have these fields, quantum fields, which are also concepts, numbers. That's all they are. So we have excitations of numbers, and we have energy bundles, which are called particles. Okay? When the interactions are strong, or when the field interacts with itself, the particle concept needs to be discarded. So even we have this situation where the particle is gone. We have no particles. Okay, so the bottom line, there are no particles anymore in quantum mechanics. Now it's quantum field theory, which has replaced the discrete bundle with which we started quantum mechanics. And the great irony is that in the end, we end up with no quanta at all, just interacting fields that obey weird rules of algebra. Oh, great, we understood quite a bit. It's absolutely stunning that after 100 years, these are the answers you get. You have absolutely no idea what they're talking about. Okay, all they have is math. And they say, well, we can describe it mathematically. Yeah, maybe you can, whatever you're describing, but if what's in that invisible world are not particles, all your math is worthless. 100 years of math is worthless. And don't tell me that technology and blah, blah, blah. No, technology doesn't prove theories, doesn't tell you what's in that invisible world. So technology will not tell you the fact that we made a bomb, nuclear bomb, does not tell me that the theory that they're using to explain quantum mechanics is correct. Okay? Or that it has something to do with reality. We develop, technology by trial and error. And we don't need to know what a magnetic field is to make a bomb or to make a circuit. And we can do it. It's practical. We just look at what results we get, and based on those results, we use those features to make something. That doesn't mean we understand what's going on in that invisible world. And that's the issue with quantum mechanics. They do not understand what's going on in the invisible world. They represent it with particles and waves, both of which are irrational because the particles ain't particles. They are what? Quantities, and the waves are numbers. So that are flowing, all the way from Andromeda Galaxy. So yeah, we have a problem because none of the physical interpretations from quantum mechanics passes the test of science, let alone of physics. Okay, so here we have one of the problems, another of the problems where with the proton, and it is this. Here you have the typical proton, and we showed you a minute ago. And what's the issue? The issue is that they say, look, the proton is made of quarks, 3 quarks. And why did they do that? Well, they had to do that so that they could explain why neutrons have no charge and why protons have one value of charge, which is 1.6 times 10 to the minus 19 coulomb. And what's the problem with that? Well, here's the problem. The problem is that, they can't extrapolate that to the electron. Does the electron also have quarks in it? Is that why it's got the opposite charge, the negative charge versus the proton, which has positive charge? I mean, they were able to explain the proton and the neutron, but the problem is that, they cannot extrapolate their scheme to the electron. And so we got a problem there because, if you cannot extrapolate it, what's the point of doing that math? Because all it is math. They're saying that you get 2/3 plus 2/3 of the up quarks minus 1/3 of the down quark, and you get 1. And if you get 2 down quarks, 2 minus 1/3, you get minus 2/3 plus 1 up quark, which is 2/3, you get 0. That's math. That's got nothing to do with whether there are quarks inside a proton. And the question is, okay, if that's your scheme, now extrapolate that to the electron. Show me why the electron is minus 1.6 times 10 to the minus 19 coulomb. And that's the problem. That's the first problem we have, right? But that's the least of our problem, or one of the least of the problems. Here's a bigger problem still. Here it is. Okay, and that is that these people say that the proton is made of really gazillions of gluons and quarks, not just 3. The 3 are those 3 valence ones, the ones that are running around there, the big ones that you can see. All the others that are in the background, those are gluons and quarks and other virtual particles, right, that pop in from the void, pop into existence, and instantly, annihilate each other and go out of existence. And so you say, well, why did they need that? I mean, can't we just stuck with the 3 little quarks? No, they couldn't. Because the problem is that each one of the quarks weighs very little. It has very little mass. And you cannot explain the mass of the proton unless you put gazillions of, quarks and gluons and virtual particles in there to fill in, the volume, the ball, right? The proton ball. And what they look at is the kinetic energy of each one of these particles. They sum up all the kinetic energy at any point in time, even though, they come into existence and go out of existence immediately. And all these quarks and gluons and virtual particles that are popping in from the void, and their kinetic energy is summed up, and that's why the proton weighs more, than each one of the quarks, the 3 quarks that make them up. So they had to explain that. In other words, more magic. All they did was just include, particles taken from heaven, right, that they included in there because they needed to explain the mass of the proton and why it has more mass than each of its constituent quarks. Okay, so they could explain the charges with the 3 quarks, but they could not explain the mass. And so that's why it's full of all these particles that pop in from the void. And so what they say is that these particles constantly come into existence and out of existence, that they annihilate each other, right? And so what does a normal human being, a rational human being, understand by that? Well, what you're saying is there was a man, right? And he turned into a spirit and disappeared. Okay, that's what it is. So I saw the man in front of me, and suddenly he turned into a spirit, disappeared. And suddenly he appears again, and then disappears, like a ghost, right? So he's here now, and now he's not here. Okay? What did he turn into? Well, he turned into empty space, I hope, because that's what, disappearing means, vanishing means, right? And so the problem there is that these people, here, let me put this on this side. What these people have is this word annihilation. But annihilation doesn't mean annihilation. It doesn't mean vanishing, disappearing. It doesn't mean coming into existence and going out of existence. It doesn't mean any of those. Okay? What it means is that two particles turn into two particles. That's what it means in quantum mechanics. Okay? And what they have is these particles which turn into two particles, which again do some fancy footwork there, mathematical footwork, and turn into two more particles. So particles turn into particles, meaning that inside a proton, all these virtual particles, virtual gluons, virtual quarks, they never disappear. They're always there because they only what they're doing is turning into something else. So they're always there. They don't disappear. They don't go out of existence. They don't annihilate. They don't vanish as, the mathematicians would like to insinuate with their language. They're always there. They turn into something else. That's all it is. But you always have all these particles inside there. So, it's not like there's only 3 quarks. No, there's gazillions of quarks in there at all times. And so what do we have now? They started with 3 quarks to explain the charges for the proton and why the neutron doesn't have a charge. They cannot extrapolate that to the electron. And now we have gazillions of gluons and quarks in there, and they're all the ways there as something. So, in fact, they have to be in there in order to justify the constant mass of the proton, because if they disappeared, they would take their mass with them, I would assume, right? But no, they have to be in there as in some way or form. And so, then we don't know what a proton has inside it. It just has gazillions of whatevers. That's what it is. And they have to put it as a wave as well, so that only complicates things. But a good one there is the last one there, the pion. Okay, pions are important because now they had to explain something else, and that's why protons, which are positive inside the nucleus, don't push each other away. You take 2 magnets, positive against positive, they push each other away, and that's what a proton should do. If you have 2 protons or more inside a nucleus, why don't they repel each other? And so they had to explain that, and the way they do that is using quarks and gluons. Now, outside of the proton in the form of pions, what is it? Pions. Well, they're outside, they're pions, and what they do is they compress the protons against each other. So we have not only quarks and gluons inside the proton, we also have them outside in the form of pions. They had to do that to explain why the protons don't repel each other. So we have more and more holes that they're plugging with just irrationality, with magic. That's all it is. It's called magic and nothing else. Okay, so that's what they do. They have these pions, and here I illustrated that the other day. Okay. By the way, here, these are the virtual particles. They pop in and out of existence, they say, but see, that's not true, because virtual particles simply are pairs of particles that turn into more particles, which turn into more particles. So that image that you see there is incorrect. They do not vanish. They do not turn into empty space. That's what I'm trying to say here, okay? When you turn into empty space, you stop being an object. You lost length, width, and height, and now you're space, a vacuum, nothing. That we can all understand. Say that he disappeared, Bill disappeared. He's no longer there. But if I turned into something else, I didn't disappear. I just morphed into something else. Okay, so that's different. And so here you have the protons repelling each other. Okay, and they push each other away, right? Why doesn't that happen? Well, here you see why not. Okay, because they are pushed together by the pions, which are made of primarily made of gluons and quarks. And so, but I thought the gluons and quarks were inside the inside the neutrons and protons. And yeah, they say they're in there, but somehow they come out of there and are able to push the protons against each other. And I'm assuming they also push the neutrons against each other. Okay? So that's the magic. That's how it's all explained. See how easy it is? Magic explains everything. And they say that's our math. Yeah, your math, if you're doing math for stuff that doesn't exist, your math is worthless. You have to explain the theory first, and then you can describe it mathematically. But if you go out there and do a lot of math for stuff that doesn't exist, leprechauns and, unicorns, well, then your math is worthless. So all this work that they've done in the last 100 years has ended up in nothing. They cannot explain a single phenomenon at the atomic level or below, right?